Thank you very much for the invitation. It's been honor and great pleasure to be here. It's my first time at Bengaluru and ICTS here. I was amazed by the beautiful campus and this fantastic weather. So I heard the altitude is high, like 900 meters or so, because that makes it even cool to be here. So today I'd like to, it's been really a few even years that I last time used this big blackboard and speak in front of people. So my board writing skills have decreased a lot in the past few years. I'll try my best, but please bear with me. I might write like straight, but I'll try. So today I'd like to talk about structure and rigidity of diffeomorphism groups. So the main motivation is to introduce this fascinating object called manifold diffeomorphism groups and what we can talk about it algebraically, dynamically, and also topologically, and possibly some analytic information too. And in the spirit of the conference, actually I'll state a theorem about something called regularity rigidity. And if you look at it, I hope I can talk about some detail about the proof, but in the core of the proof, it is a probabilistic argument that solves the main part of the theorem. So hopefully I can talk a little bit about that probabilistic argument and how it is useful to use such a probabilistic argument in purely topological problem. Yeah, do I sound better? Yeah. Is it? Yeah. Okay. Yeah. Is it better? I'm not sure. Probably. Yeah. Is it better for me to use microphone or it's? Okay. All right. All right. Yeah. Oh, I see. I see. Okay. Thanks. All right. So for that, I'd like to talk about the structure of diffeomorphism groups and how, or there are too many things too many structures do the groups have. So I'd like to introduce some viewpoint on the rigidity of such groups. Let's see. So this is joint work with Thomas Cuberta and partially with Javier de la Nuez Gonzalez. So let me introduce the players first. It is manifold diffeomorphism groups. As I said, my board writing skills might have decreased a lot in the past 3 or 4 years of like being stuck at home. So please let me know if I write too small or writings are not legible. So manifold diffeomorphism groups. So today, let's say M is smooth boundaryless manifold. Although eventually we'll just drop these conditions like smoothness or boundarylessness conditions. Then you can talk about its homeomorphism group, which is collection of all the homeomorphisms, which is abbreviated as these two tildes. And this is certainly a group, right? So actually, what is a group? If you take anything in mathematics and collect all of its symmetries, it becomes a group, right? So that's the original definition of a group. In particular, if you collect all the topological automorphisms of M, then it's certainly a group. And it has many, so it can be regarded as purely algebraic object group. It has many other interesting subgroups. You can also talk about homeo 0 of M. So it is, if you collect anything isotopic to the identity. So let's just assume compact as well. So because when you talk about like, so that we don't have to worry about the topology, the ambiguity on the topology of the group. Then this coincides with the identity component of the homeomorphism group when given with compact open topology. And you can also talk about, say, volume preserving group if mu is a measure or volume. And there's also a notion of a good measure, which assigns positive measure for all open sets. So we'll talk about that later. And also it has many diffeomorphism groups, right? So diffeomorphism groups. So this is collection of all the C1 diffeomorphism groups, differentiable and derivative is continuous. And this has smaller groups, say diff2, and so forth. And diff infinity. C infinity diffeomorphism group M, which is intersection of the CK diffeomorphism groups. And also you can talk not just that, you can also talk about Helder continuity of diffeomorphisms. In other words, you can collect, say, real number R, where R is written as, say, K plus tau, where tau is between 0 and 1 and K is integer. And if R is defined to be as all the diffeomorphisms, CK diffeomorphisms, such that its kth derivative is tau Helder continuous, right? So you can write down the definition. So supremum of locally, so everything is compact. So this definition is fine. If you take CK derivative at X, then this is a matrix multilinear map. So you can subtract G and take the norm, compare this manifold distance to the half power. So compare the operator norm, take the difference, and compare with the half power of the distance, and is finite. So this is the definition. This is nothing more than just definition of kth derivative is tau Helder continuous. And it is a interesting exercise, actually elementary but interesting chain rule exercise to verify that this is a group. So not just countably many groups, but you have uncountably many. Real number, many diffeomorphism groups inside homeomorphism group. And as a group theorist, when you're given it many groups, you want to know about their algebraic properties. So the theme that I'd like to address is algebraic properties of these groups. And hopefully I can give some justifications to study the algebraic aspects of these groups. These are topological objects by definition. Why do you want to study them in the viewpoint of algebra or group theory? Well, that could lead to some interesting mathematics. Okay. So there are, largely speaking, there are two aspects. So if Rm as groups. So one direction is universal aspects, namely some properties, some group theoretic properties that hold generally for all such diffeomorphism groups. So one particularly interesting result is simplicity theorem. Basically, these groups, if you take some conceptually minimal subgroup of these groups, then they become simple. That is, so the R, basically, if R of, say, C0, I'll explain what this means, of n-dimensional diffeomorphism group is simple for 0 R infinity such that R is not n plus 1. So this is the result. So first of all, the credit first, because especially this is recorded. So R equals 0 case is due to Anderson in 1962. And Thurston established this for R equals infinity case in his 74 paper, and matter proved for the rest. R is not n+1 for 74 and 75. And also Epstein reproved Thurston's result using Matter's idea too. And here, so C0 means a collection of compactly supported. So it's basically identity component in the C0, in the compact open topology. Compact, so M is not assumed to be boundaryless in this case or anything. So M is not compact, M is just a possibly non-compact, possibly with the boundary. In this case, in this theorem, compactly supported and isotopic to the identity through compactly supported isotopy. So it's kind of mouthful, but you know what this means. And with a suitable topology on this diffeomorphism group, this simply means identity component of M, especially when M is compact. So this is certainly a normal subgroup, right? So if you collect, if M is not compact, if you collect all the compactly supported ones, then it's trivially normal subgroup. And isotopic to the identity, the same. So C0 is normal subgroup, but it's saying that it's minimal. There are no more smaller normal subgroup, and it becomes simple. So in some sense, these groups are very big. And R equals n+1 case is still unknown. So in particular, open question is famous open question is if 2 of S1, and obviously you have to take orientation preserving, is simple or not. So this is still outstanding question in this field. But so that's why R equals n+1 is excluded in the theorem. So there's nothing wrong with R equals n+1 except that it's not proved. So we don't know. It is still possibly it is still simple, but people have no idea. And also regarding that open question, there is a very interesting 2-page paper by Matter proving that if so collection of all the C1 diffeomorphism groups whose first derivative has bounded variation and compactly supported is not simple. There is a homomorphism from this group onto the real line. The proof is actually very simple. It's very interesting to look at. It just uses almost the definition of bounded variation. So bounded variation, what does it mean? It means that it is the distributional derivative, right? It is something like derivative in the sense of integral. And using that measure, there's a singular part and regular part. And if you only look at the singular part, it defines a homomorphism from this group to the real line. It's really 2-page paper. So what I'm saying is like, I don't have any opinion about the validity of this conjecture, whether it's simple or not. It could be simple, it may not be simple. So that is one aspect. Yeah. n+1, right? So group theoretically, it is not special at all. I cannot find any distinction. But if you look at Matter's proof, it is very special. Because what is his idea? So basically this theorem is almost, one can immediately reduce to this to the theorem that diff R of R to the n completely supported is simple. So you have only to prove this. And then you use fragmentation to fragment the diffeomorphism into smaller ones supported in charts. And you prove that this is simple, this is perfect, so everything works fine. So we need to prove that this is simple. And his idea, so Matter wrote basically two papers, very similar, but in the opposite direction idea. So when the regularity is larger than n+1 and smaller than n+1, this kind of very similar but opposite direction idea. The idea is that if you have some element here, so let's consider, say, a real line diffeomorphism, then complexly supported. Then we kind of say expanded a lot. So conjugate. So say suppose it is supported in -1 and 1, then conjugate that it is supported in say -billion and +billion. Okay? And then you kind of average the action. It's not just the action itself, but slightly perturb a little bit, perturb a little bit, perturb a little bit. And then you average it so that it acts on the circle. So there is a not homomorphism, but some operator from real line diffeomorphism group to the circle diffeomorphism group. And you average it, and then it somehow gives you a nice decomposition as a product of commutators. So it gives you the perfectness of the group. But for that to work, the regularity plays a role. So if R is larger than n+1 and R is less than n+1, this averaging operator does the opposite thing. So if it is very smooth, I think you have to increase a lot and average it. And if it is not so smooth, then you have to like contract it and average it. So it's like, so it's in the argument. So his method's averaging operator takes the regularity as an input, and this operator does the opposite thing when it is very smooth or if it is not very smooth. So this kind of roughly explains why n+1 is the critical exponent. Yeah.
But then as groups abstracting, right?
Yeah.
Look at them as topological, because is it easier to see that the topologic is?
So yeah, you can talk about their H1 as topological group, but I think that is equivalent. I think that is equivalent, right? So there is so there are two H1s, right? H1 as a discrete group and H1 as topological group, right? But I think you can reduce the topological group, at least for the smooth case, or possibly for this lower regularity group. There is a isomorphism between H1 of topological group homology and H1 of discrete group homology. So I can find the reference for you, I think, yes. So I believe there's yeah, we can talk about it later, yeah, but yeah, I believe, yeah, that's what happened, yeah. So, right, so yeah, what is the bottom line? Bottom line is there is some universal aspect, and also Matter's proof is actually very, very interesting. And then the beauty is actually in the detail of the proof. So if you're interested, there is a some survey article on matters proof that is written by myself and Thomas and another person, Jaewon Chang. And we worked out all the details for the one manifold case. So it's, I believe that could explain more things about why this M+1 of critical phase exists. Okay. Then, right, what was I doing? I was trying to find the eraser actually. Right. Oh, so this is the eraser. Yeah. And some individual aspect, actually, that is what I'd like to focus today. Is one thing that I'd like to talk about is something called Takens-Filikevich. So these are they didn't work together. So Takens got 79, Filikevich 82. So it's a combination. So Takens considered most important case, say Sang-hyun case, and Filikevich proved the general theorem. So what is it? So M is just in this case, any manifold, say smooth, and say boundaryless. And say P and Q are positive integers. 0 is fine, but for the simplicity of the presentation, I'll just consider positive integer case. And consider, so suppose, so if, so M and N, sorry, M and N. So if P of M is abstractly isomorphic, say phi, isomorphism, as if Q of N. So if there is an abstract group periodic isomorphism, then this is induced by diffeomorphism. Then P equals Q, and there is a CP diffeomorphism, P diffeomorphism, such that the group isomorphism is induced by this thing. So for all G in diff EM, you have M to M, N to N, and you have W, G, and phi G. So, I mean, in word, this simply means that W conjugate. The phi is induced by W, or W conjugates these two diffeomorphism groups. So if you look at it, this is kind of amazing because the group theory remembers smooth structure of the manifolds. So, and you can recover the regularity and manifold, because in the hypothesis, we didn't really assume anything about M and N. We don't assume even anything about their dimensions, but it turns out that the dimensions are the same and the regularities can be detected by the diffeomorphism group. And in fact, you don't really need the full diffeomorphism group. You only need isotopic to the identity part of the diffeomorphism group also. That is a variation of Takens-Filikevich theorem. And slightly demystifying this theorem is that actually this is an easy consequence of two interesting theorems that appeared about the same time. So one is Rubin's theorem. So it is published in 1989, but apparently actually at least the existence of this theorem was mentioned in Filipkevich's theorem. So what is it? So this is that this if you have a isomorphism between, so say you have a homeomorphism group, G1, G0 and G1 in the homeomorphism group of, say, Xi, I is, say, 0 and 1. And this is locally compact Hausdorff and perfect. Perfect simply means no isolated points. So you have two groups, G0 and G1. And we assume these groups are locally dense. So Gi are locally dense. I.e., this simply means that whatever open neighborhood you consider, the local stabilizer has dense orbit. That is, you consider G, let me completely write it down. Collect all the homeomorphisms supported in U. That is, G outside U is identity. Or see, we can use support, right? Support is fine. Right? So this is a group. So take the orbit. Then this is not nowhere dense. In other words, if you take the interior of the closure, then this is not empty. So this is definition of locally dense. Okay. So in other words, if you consider so-called rigid stabilizer, any orbit of rigid stabilizer has interior somewhere. So somewhere dense, right? The opposite of nowhere dense. So in other words, it is like sufficiently many elements locally supported. For example, you can consider, right, any, say, C infinity compactly supported group is locally dense. Or any PL diffeomorphisms, locally dense. Or even you consider, if you know what this is, Thompson's group F. Homeo of open interval. It is not locally dense at the endpoints, but open interval, it is locally dense. So many groups that we are interested in have this property, and this is hypothesis. So if you have two groups locally dense, and they are isomorphic, say P is isomorphic. So these are three hypotheses. Then there's a homeomorphism conjugating V. As on the diagram on the left. So what does this mean? So you have some reasonably nice space, locally compact Hausdorff perfect. It's not too much to ask. And locally dense, it is sufficiently big local stabilizer. And if two groups are isomorphic, so you can just assume that there's one group acting on two spaces. It's the same thing. Then actually, the spaces are homeomorphic and the actions are conjugate to each other. So Rubin's theorem gives you C0W right away, like for free. If you know this theorem, then in the statement of Takens-Filipkiewicz, you immediately have W as a homeomorphism, C0. And the remaining part is smooth conjugation problem. You have a topological conjugation. Can you upgrade it to a smooth conjugation, CP map? And more precisely, what Takens did was has solved the smooth conjugation problem. So in the case of P and Q are infinity, and if you are given with homeomorphism C0, Takens gave a method to find C infinity diffeomorphism conjugating the given isomorphism. But in general, there is a another thing, I told you that Parkins-Philip-Kevich theorem can be demystified as a easy consequence of two big theorems. One is Rubin's theorem. The other is Buchner-Montgomery theorem, classical result. Theorem. So this is, I think, 1952, or actually, it's even earlier. It's 45. So sometimes this is misattributed as Montgomery-Zippin theorem, but it appears in Montgomery-Zippin book. But it's not their theorem. It's just stated and proven carefully in 1952 book. So what is it? So this gives you, so our problem is we have a C0 map and we want to upgrade it to smooth map, CP map. And Buchner-Montgomery theorem is doing that. So if you have a, what is it? Hypothesis, if you have a Lie group acting on a manifold, and this is a CK group action. It means that for each group element, the action is CK diffeomorphism. But the action may not depend smoothly on G. It only depends on continuously on G. So the map G, X to G dot X is only C0. Then the conclusion is G dot X is CK. So in some sense, it's kind of magical. And it is not exactly Hilbert's fifth problem, but in a similar spirit. So Hilbert's fifth problem is if you have a locally Euclidean topological group, then it is automatically smooth. So that is Hilbert's fifth problem. So in this case, we already know that G has smooth structure. But the question is about the action. And somehow this CK differentiability on the space is transferred to the CK differentiability on the groups. What is K is integer and at least one, yeah. Yeah. Right, that's right, yeah. So, I mean, I can say just roughly how is it relevant. So now we have C0 map by Rubin's theorem. Right? And now we want to prove. So W is already given. We are not changing W. We just want to prove that W is CP map. So for that, you consider a chart on M. Right, so look, so Rn acts locally on M by translation or something conjugate to translation locally. And this is CP map. Right, so what is CP map? So Vx is mapped onto some, say, I'll call it translation V by X. Is CP. Depend CP on V and CP on X. Right. And this group action becomes some mysterious group action. Some mysterious group action by phi, because phi maps any group element, the group element on the target. And this is at least, it depends on continuously on V, and it is CQ on the space variable. So by Montgomery-Zippin theorem, this Y maps to phi TVX depends smoothly on V as well. So that's kind of a mysterious outcome of Buchner-Montgomery theorem. So in the target, the Y goes to phi TV of Y. This depends smoothly on V as well. So it gives you a chart on N, and you can argue that this is really diffeomorphism. Yes, my intention is I not going to the details of the proof, but show generally how this Takens-Filikevich theorem can be viewed from as a consequence of these two theorems. And so what does it mean? It means that you have it means that so you have a pair, manifold and real number, then this gives you a diffeomorphism group. But somehow you can recover manifold and real number from pure group theoretic information of diffeomorphism group. So you have a topology and analysis, which is the regularity from a purely group theoretic object, diffeomorphism R. And so one can view this phenomenon as in the viewpoint of rigidity. So there is a very fruitful and influential direction in the theory of lattice to study rigidity of lattices in Lie groups. So this goes back to Andre Vayu for the so-called local rigidity of lattices in Lie groups in the co-compact case, and Garland, Raghunathan, in 1970, and Mostow and Margulis. So after a combination of the result, the key sense of Margulis superrigidity can be phrased as follows. So where I'll just omit most of the hypothesis. Under suitable hypothesis, if you have a lattice, in other words, discrete finite volume subgroup of a Lie group, where some mild hypothesis like no compact factors and rank is at least 2, and you have if you have some arbitrary homomorphism in another Lie group, okay, then there exists a representation from G into G prime extending rho. So this is as a group, this is just simply a finitely generated group, no topology involved at all. But you only consider the group theoretic property, that is homomorphism from gamma into another Lie group, that somehow gamma remembers about G and produces homomorphism from G into G prime. So you want to recover this topology analysis from some purely group theoretic, even finitely generated subgroup of that. So the question is, can you do a find a similar rigidity result for subgroups of diffeomorphism groups? So some finitely generated group inside diffeomorphism group of some regularity, such that whatever homomorphism you consider, does there exist such that there exists some extension from diffeomorphism group to another? N. Yeah. Thanks. So somehow purely group theoretic and even in some sense finitistic object, algebraic object, can remember the whole diffeomorphism group. Can it recover diffeomorphism topology and analysis about them? So of course, I cannot prove such a statement in full generality, but I'd like to state some things in the similar spirit. Yeah. Right, so it's a good question, but I believe you have to define what it means by quasi-isometric as well, because this is big topological group. So the quasi-isometry should be in the sense of this Rosenthal on topological groups. Yeah. And then I do not know, but I believe there's a good chance that quasi-isometry can recover. I do not know. Right, so to solve such a problem, so we have to look at group. So there are, largely speaking, so three components. So one is group theory, the other is dynamics, and the other is topological analysis. And the things that I'd like to talk about to establish results toward that direction is interplays between these three different objects. So between dynamics and group theory, I will need to consider probabilistic, long-term behavior of orbits. In dynamics and topology analysis, so we can basically the catchphrase is smoother diffeomorphisms are slower. So what does it mean? Well, it basically means that if you have a C20, C25 smooth diffeomorphisms, then you have a better control on the orbits, progressions of orbits. And group theory and topology is basically this, right? So finitely generic groups. And remember, topology and analysis, regularity. Manifold and regularity. Yeah. This commutator is perfect. So the open question is it perfect or not? So is it not known whether it is perfect or not? So it is known that its commutator is perfect. And simple. Commutator is simple, right? So all you have to show is the group is perfect. Right? Okay, so right. So regarding this rigidity of finitely generic subgroups, something that I'd like to discuss is the following. That say, let's go to theorem A. That so it's about actually one manifold. So say M1 is compact connected to one manifold. Okay. Then for all real number, there is some finitely generic groups, say GR and HR. such that the following hold. So GR is CR diffeomorphism group, and it never embeds anything higher. In fact, one can prove that one can actually require that GR as a simple commutator group in the similar spirit. So any homomorphism will have abelian image. And HR is similar, just a kind of dual. So it is almost CR diffeomorphism. So anything smaller. But it never embeds into HR, defined M1. So plus means orientation preserving. So these are finitely generated groups, and we can even impose any some other nice conditions on HR, like having simple commutator groups. So any homomorphisms will be greatly restricted. So in some sense, these groups can remember, at least for the case of one manifold, the regularity. So purely algebraic property, purely group theoretic property can remember the real number R. And most of them will be infinitely presented, right? Because there are only countably many finitely presented groups in the world, right? And for each real number, we define the group. Therefore, most of them will be infinitely presented. Yes.
The homomorphisms between V groups are well understood. Is there a similar thing on the diffeo side? Like, you told us a little bit about.
That's an excellent question, but not as much as we want. Not as much as we want. So there is some very nice result due to Lei Chen and Katie Mann, that the homomorphism under certain conditions, like the target dimension is larger than twice of the source dimension, or so under certain conditions, you can classify such homomorphisms of diff K of M acting on another manifold N by, say, CP. Then in many cases, the actions can be classified. So what you can do is either consider like the embedding of the manifold or embedding into some configuration space of the target manifold, and basically and some composition of that, and that's it. So there is a certain orbit classification theorem. But it's not complete understanding, I believe. Yeah.
What was the assumption?
I cannot remember it right now, but there are some assumptions. Like sometimes you want some transitivity, sometimes you want some hypothesis on the dimension. For example, like target dimension is more than twice of the source dimension, for example. Like that, yeah. So yeah, it's a very interesting direction to classify possible homomorphisms between diffeomorphism groups also. Okay, so any other questions? Right, so this theorem tells you that find the group theoretic property of finitely generated group can remember the regularity, the real number. Somehow analysis can be recovered from group theory. It's very explicit, very explicit. So of course it is infinite construction, but so there are like 7 generators or something. So it will actually, yeah, we will each of the generator will be just defined separately on infinite many disjoint intervals. And on each interval, it is just integral of something. It's very explicit. And kernel is explicit as well. So how do we prove such a thing? Well, it is a consequence, actually immediate consequence of this theorem B. So I can at least deduce theorem A from theorem B today. So theorem A, I'll just assume, consider I case, interval case. Okay. Then what is it? So I'll just prove just part one. So that can be deduced by this theorem. So for each real number, let's define some universal group, say G star, or is some group. The specific presentation of this group doesn't really matter for today's purpose, but there is some group, okay? Say Baum's-Lach solitary group of 1, 2, say, I think star Z. See, so I think this is enough for today. Right. So actually, yeah. Some group. The presentation doesn't really matter, but anyway, some group such that for each real number, we will construct some representation of G star into CR diffeomorphism group of interval, okay, which will be C infinity inside. Okay. So this non-smoothability appears at the endpoints. So in the at each interior point, it will be C infinity smooth, such that whatever higher regularity representation you consider, of course, it should be non-trivial. Okay, of if S plus 0, 1, there is some element inside kernel of psi, but not killed in kernel of PR. So that's all you do. Right. So we will, So actually, we will not algebraically define this GR. GR will be taken as the image of this part. So we will construct some representation of this group into CR diffeomorphism interval such that whatever higher regularity you consider, higher regularity representation you consider, you can somehow control the derivative. Using smoothness, you can control the orbit so that there will be some kernel of the new representation that is not killed by VR. So this is just purely algebraic trick. So I can explain why theorem B implies theorem A. This idea has been used in the literature before several times. So what do you want to prove? So we want to prove that GR can never embed into DFS. So assume for contradiction that this group GR, so phi G star embeds into if S interval, say. Assume for contradiction that this group embeds into some higher regularity diffeomorphism group. Okay. Then we have this G star surjectant here by PR. And there is some mysterious embedding into TIFR. So consider it as just psi. Okay. Then there must exist some element. And this is a contradiction, because then, well, psi is trivial, but it cannot be killed by VR, and this is assumed to be injective. So this is contradiction. So this is just purely algebraic trick. So what you do is you construct nice representation. You don't really have to try to, so I mean, the point of giving this proof is this. So you cannot really define GR algebraically, like by infinite presentation or something. Rather, you just define it as some maps into just choice of maps in the diffeomorphism group and show that property in theorem B. So that is something that I'd like to do tomorrow and Thursday after giving some background and other relevant results. Yes. All right, so S1 is side, yeah, I kind of omitted the explanation of S1, but S1 can be deduced from this case. So this is really the basic case. And then you bootstrap so that if so, what you do is you find some circle diffeomorphism group so that it's say some nice subgroup all these fixes a point and apply this argument for that subgroup. So you can deduce the circle case from this, which requires some trick. Yeah. That's a great question. That's a great question. Right, so I do not know whether the actions are minimal or not. I don't know. And actually, I'll talk a little bit about that aspect because it's a very good question. That is something relevant to something that I'd like to talk about. Maybe not today, but tomorrow. Okay, so so this is about regularity rigidity, and for general manifolds, I'd like to hopefully talk about the following results. So today I'll just overview what I'd like to talk about for the rest. So in this case, what we can say is the rigidity in the case of homeomorphism groups. So for that, let's say M and N are topological manifolds. Yes.
As you change your.
Oh, right, it's G. So this is not universal. That's the whole point, right? So whatever G you choose, you can try to make it. You can try to kill it, but then there will be some other element in the kernel here, and you can like find a representation that kills it, but still some other will survive. Right. So whatever non-trivial element you consider, it survives in some representation. So again, what does it mean? So whatever non-trivial element you consider in GR or G star, you want it to survive it. Survive. I believe that is possible for some possibly silly reason, because you have a, say, CS diffeomorphism group, you can kind of juxtapose another action that only cares about that element. So make sure just, you don't really care how big the kernel is. You just make sure that element survives. And you just consider 0.5, you consider some nice section, and 0.5, you have new action here. And you want that if time of G0 is not trivial for a given G naught. Because these groups, because that should be possible. Because first of all, this whole group is obviously embedded into the infinity of the real line, but not compactly supported. So I believe you can make sure each element survives. So yeah, if you ask me, I believe that is doable. So possibly a relevant result is that so this is not. I'll have to think about it. I think this is a legitimate question, which has a good chance of being true. You will have to know a bit more about G star. But actually, that may not be true. So what is the theorem? So there is a theorem by Bonatti, Monteverde, Navas-Rivas, proved in 1917 that whatever representation you consider Z cross BS1, 2 into C1 diffeomorphism group of interval, let's call this as C cross A and E, where BS1, I didn't define what BS1 is, but this is like affine groups, A, E, A inverse is E squared. They prove that a support of C should be disjoint from support of E. So this I'm not sure. So something is necessarily implied regarding their support. So it is, yeah, I don't know actually, I don't know. That's a good question. Something might be imposed so that some element must survive. I don't know. Yeah. But I think there's a definite chance that that is true. So yeah, let me just state some of my wild guesses. So like, for example, writing darting groups. So for all, say, writing darting group, does there exist a representation of A gamma into, say, C infinity group of interval such that PG is non-trivial. And I think this is true. So this is, I think, true. So I can even include this in my paper that you can make sure that this element survives in some symphony representation. Regularity group. Yeah. And this is really like using direct product and free product structure. So I think you can use that's why I told you that you can use similar argument to show that any element will survive. But I haven't worked out the details, so I cannot tell you for sure, but there's a good chance that the same argument works. Well, actually, yeah. Yeah, I think, yeah. So you can use just, so this is right in there. So you can use direct product and free product structure to make sure that every element survives. Okay. Right, so regarding topological manifolds, what I wanted to say. So here I really didn't assume anything, like even TL or triangulable or smooth anything, just nothing is assumed. Then if all I want to say is if the homeomorphism groups are elementarily equivalent, so I'll say what this means later, then they are homeomorphic. So this is a generalization of Anderson's theorem. So Anderson's theorem, I explained, is that if you have a group isomorphism between two homeomorphism groups, then the manifolds are homeomorphic. But in this case, you don't even assume like anything about the manifolds like smooth or boundary or triangulable. It's just they are elementary equivalent. So what does this mean? This means that the first order sentences which are true in the groups are the same. So first order means like you use quantifiers and logical symbols such as and or and this group composition and inverses and equality. So any sentences made of this, like for example, abelian groups, any two elements will commute, or rank this nilpotence class 2 group, Heisenberg group, like any iterated commutator of length 3 will die, something like this. So if you have if the sentences are the same, then they are homeomorphic. And why do we care? Because it gives you countable example of rigid homeomorphism group. Because it is almost abstract nonsense that any group, any topological group is elementary equivalent to some countable subgroup. Because what is the theory? Theory is just a collection of sentences using these symbols. So there are only countably many sentences in the world. So whatever theory you consider that is realized by some countable subgroup, it is so-called downwards column theorem. So there exists some countable subgroup such that anything that is true here and vice versa. So this is elementarily equivalent subgroup. And same thing for this thing. Some countable subgroup, which is elementary equivalent. So these groups are elementary rigid, although they are countable. So countable, but they capture all the first order information about the surrounding group. And these groups somehow mysteriously remembers the topology of M. So for each manifold, there's a countable subgroup. For each manifold, there's a countable subgroup. And these groups are group theoretically isomorphic if and only if the manifolds are homeomorphic. So that will be the corollary of this theorem. So hopefully I can talk a little bit about theorem C in the last part of my theory, my talks. Okay. how explicit is you mean this thing? Right. So it is in some sense very explicit. So right. So theorem C will be a corollary of theorem D. That for all manifold, there is a sentence called, say, I am M. In the theory of homeomorphism group of M, this is the name of the sentence, I am M, right? Or you want to call it just phi of M or something, such that yeah, I'll just call it phi M, okay? Such that phi M appears in the theory of other homeomorphism group if M is homeomorphic to M. First order theory, yes. Yes. So you can only quantify over elements of the group, not subsets of the group. And this, so there's some recursively defined, somewhat explicit formula which detects the manifold. And theorem C is trivial consequence of this thing because phi M only appears theorem of M. And anything homeomorphic to M. Okay. Right, no, right, nothing at all, right. No topology, like no PL, no triangular, no smooth. Yeah. So the whole purpose is, as I see raised, so there is a, so VM is trying to express that I am M. So some group theoretic expression such that the manifold is M, homeomorphic to M. So that is so naively speaking, that there will be just some second order statement that M is homeomorphic to M. But the existence of homeomorphism is second order statement. So you work a little hard to make sure that it's a first order sentence on the group theory. Any questions? Okay, yeah, sure, yeah, right. So, right, so I have a 2 minutes remaining. Right, so I'll just make one definition and that's it regarding this theorem A and B. So that we can start with recalling this definition tomorrow again. So what I'd like to propose to study is something called critical regularity of some manifold of a group. So this will be the largest possible regularity that G embeds into if R of M. So defined as negative infinity if G doesn't embed into the even mu. So this is some real number or extended real number. Could it be negative infinity, possibly infinity, or some number between them. And the thing that I'd like to propose to study is this group invariant. It's obviously isomorphism invariant. So tomorrow I'll talk about some cases that critical regularity could be either negative infinity or infinity, could be 1, 1.5, 2, or for the groups that I described today of interval of GR will be exactly R for each real number R. So this is some group theoretic invariant that I'd like to study tomorrow. Okay, I'll stop here. Thank you very much. Yes.
One case. So, how
How? how abundant?
This is one.
Right, right. So, right. Well, so one thing that I can tell you right now, written in the paper, is there are uncountably many pairwise non-isomorphic examples of such a GR. But of course, you can, you want to impose some other interesting geometric or group theoretic properties. That could be an interesting question. But at least I can say that there are uncountably many pairwise non-isomorphic examples. Right, yeah.